enhances the FR57xx architecture and core peripherals. The MSP430X CPU incorporates features specifically designed for modern programming techniques such as calculated branching, table processing, and the use of high-level languages such as C. This CPU can address a 1 megabyte address range without paging. The MSP430X CPU is also completely backwards compatible with all other MSP430 CPUs. The MSP430X RISC CPU includes features such as an orthogonal architecture, full register access including program counter, status register, and stack pointer, single cycle register operations, large register file that reduces fetches to memory, a 20-bit address bus that allows direct access and branching throughout the entire memory range without paging, a 16-bit data bus that allows direct manipulation of word-wide arguments, a constant generator that provides 6 of the most oftenly used immediate values and thereby reduces code size, direct memory-to-memory transfers without intermediate register holding, and byte, word, and 20-bit addressing. This slide shows the operating modes and the reset sources for the MSP430. The system reset sources include a brownout reset, a power-on reset, and a power-up clear. Different events trigger these reset signals, and different initial conditions exist depending on which source triggered the reset. Similar to the F5XX flash family, the FR57xx features 7 operating modes for standby operation ranging from LPM0 to LPM4.5. The modes are selected based on the need for clock frequency, power requirements, and the type of peripheral that needs to be enabled while in standby. This slide shows power numbers for modes such as LPM0, LPM3 and 4, and LPM3.5 and 4.5. LPM0 is an ideal choice for applications using a high-frequency timer to trigger an interrupt, allowing the CPU to be turned off while providing for a fast wake-up. LPM3 is the preferred mode for the real-time clock and allows the operation of the RTC crystal while consuming less than 7 microamps. In LPM4, all the system clocks are turned off and device wake-up is possible only from an external interrupt such as a switch triggering a port pin. LPM3.5 and LPM4.5 are more specialized modes that allow the digital core to be turned off while retaining minimum functionality, allowing the device to hibernate. This mode is also known as deep shelf mode. An example application where this mode is used is to store battery-powered products in warehouses before shipping to an end user. The products are required to consume extremely low power while maintaining, for example, the time or the ability to wake up from a switch interrupt. This slide shows a quick overview of the wake-up time comparison from different LPMs across MSP430 families. As you can see, LPM0 provides the fastest wake-up time at 1 microsecond. The trade-off being that the LPM0 is also the highest power standby mode. In comparison, LPM-X.5 is similar to waking up from a brownout reset and takes up to hundreds of microseconds, but this is also the lowest power mode for the 430 because the digital core is kept unpowered. For more information on accurate wake-up times, please refer to the device datasheet. PMM and Core Voltage. The Power Management Module, or PMM, manages all functions related to the power supply and its supervision for the device. Its primary functions are first, to generate a supply voltage for the core logic, and second, to provide a mechanism for the supervision of both the voltage applied to the device at the DVCC pin and the voltage generated for the core, known as V-core. The PMM uses an integrated low dropout voltage regulator to produce V-core from DVCC. In general, V-core supplies the CPU, memories, both flash and RAM, digital modules, while DVCC supplies the IOs and all analog modules, including the oscillators. In the FR57xx device, the core voltage is fixed at a single level, which makes it different from the programmable flash F5XX PMM. A few guidelines that are important to follow with respect to the PMM are: always use a 470 nanofarad capacitor on the V-core pin. Remember, the ratio of capacitance from DVCC to V-core must be at least 10 based on the recommended operating conditions for this device. The V-core pin is meant only to provide a pin to place the core capacitor. Do not load it externally or power any circuitry from this pin. The V-core pin must also not be tied to any other pin on the MSP430 device. Supply voltage supervision. As mentioned in the previous slide, the PMM module provides a means for the DVCC and V-core to be supervised. Both of these functions detect when a voltage falls under a specific threshold. When the device is powering up, both the SVS on the high side, also known as the DVCC, and on the low side, also known as the core, are enabled by default. The SVS high side remains enabled in all power modes, including X.5 modes by default. It can only be disabled in LPM4.5 to save power. The SVS low side is automatically disabled in LPM3, 4, LPM3.5, and LPM4.5. It can optionally be disabled in LPM1 and LPM2. Clock system. This slide presents an overview of the FR57xx family clock system. The main advantage of the orthogonal clock system is its ability to branch any clock source to any system clock. There are 5 available clock sources for this family. Low frequency crystal on XT1, typically 32768 Hz for the RTC. Very low power, low frequency internal oscillator that operates at approximately 10 kHz. High frequency crystal on XT1 and XT2 with a frequency limit between 4 and 24 MHz, and the internal high frequency digitally controlled oscillator, or the DCO, that can be programmed with 6 different calibrated frequencies. These clocks can be used to source the CPU clock, main clock or M clock, the high-speed peripheral clock, sub-main clock or SM clock, and the auxiliary clock or A clock. An internal 5 MHz oscillator provides timing for the ADC10 module and is not directly accessible by other peripherals. Note that the system starts up at 1 MHz M clock with the clock source DCO set to 8 MHz and the clock divider set to 8. This can be changed in the user application code as needed. Also, on failure of the low-frequency crystal LFXT1 defaults to VLO clock, and on failure of HFXT2 defaults to MODOSC. The table shown on this slide provides a listing of 6 different programmable calibrated DCO frequency settings. They are 5.33 MHz, 6.67 MHz, 8 MHz, 16, 20, and 24 MHz. These can be divided down to any even multiple using the large number of clock dividers provided by both the clock system and individual modules. While it is important to check the datasheet directly for accurate information, the DCO is approximately plus or minus 2% accurate across the popular temperature range 0 to 50 C. For the wider operating range of minus 40 to plus 85, the tolerance of the DCO is closer to plus or minus 3.5%. Note that though the DCO can work all the way up to 24 MHz, this feature is provided only in the FR5730X family of devices. In the FR5720X families, the high range RCell bit is disabled and the maximum allowable system clock is 8 MHz. FRAM controller. The FRAM controller can be considered an interface between the FRAM array and the CPU. Its main functionality is to control CPU access speeds to FRAM and to ensure that it does not exceed 8 MHz independent of system frequency. FRAM reads and writes are similar to the SRAM read-write mechanism and needs no special requirements. However, the main difference with FRAM is that with an FRAM read always requires an immediate write back to the same memory location that was read from. on the FR57xx device, this write-back is implemented inside the FRAM IP automatically and in the background, requiring no user interaction. The FRAM controller also has a built-in error correction code ECC logic that is capable of detecting and correcting bit errors. There are three options for programming an MSP430 FRAM device. They are programming via JTAG or the SPI-by-wire interface using the MSP430 FET UIF, programming via the ROM BSL, and programming via a custom solution. FRAM and the cache. To understand how the FRAM controller works in conjunction with the CPU, here is a quick overview of the system cache. The FRAM controller contains a cache with two cache sets. Each of these sets are lines which are preloaded with 4 words during an access cycle. An intelligent logic selects one of the cache lines to preload FRAM data and preserves recently accessed data in the other cache. If one of the 4 words stored in a cache line is requested, also known as a cache hit, the FRAM is not accessed and the word is retrieved from the cache. However, if none of the words available in the cache are requested, also known as a cache miss, then the built-in wait state mechanism ensures that the FRAM is accessed at speeds no higher than 8 MHz. Access to the cache is completely transparent to the user, and the usage of cache is always enabled. Since the cache is a set of registers, accessing the cache can take place at frequencies up to 24 MHz, thereby increasing the overall throughput of the system. A further advantage of using the cache is that it can lower the average power of the system by minimizing accesses to FRAM. The graph shown in the slide above shows that the average active power reduces as the cache hit rate increases. In a typical application, the cache hit ratio is about 66%, and at an 8 MHz clock speed, the average power is about 900 microamps. In comparison, at 0% cache hit rate, the average power increases to about 2.2 milliamps. Therefore, we should keep in mind that an application should be written to use the cache as efficiently as possible. For example, writing short, efficient loops can ensure optimal usage of the cache, thereby maximizing system throughput and lowering average system power. So far, we've covered the MSP430FR57xx CPU, the operating modes used in this family, and the related wake-up times. We have also reviewed key system peripherals such as the power management module, supply voltage supervisor, clock system, FRAM controller, and the cache. Please stay tuned for our next session, which focuses on the MSP430FR5739 FRAM experimenters board and the out-of-box experience made available with the board.